Okay guys, in this video we're going to be talking about the concept of solubility. And so we'll define what that is, and then we'll talk about the effects of temperature and pressure on solubility. We'll do some calculations of solubility using Henry's law for the solubility of a gas in a liquid, and then we'll discuss very briefly at the end degrees of solubility for liquid-liquid type solutions. So the main idea behind solubility is that there is a limit to how much solute there can be dissolved in a given amount of solvent. So if you think about a salt solution, so you've got a fixed amount of water, let's say a glass of water, and you start adding spoonfuls of sodium chloride to it. Well, you can actually dissolve quite a bit of sodium chloride in a given amount of water. However, there is a limit. You can't put a dump truck of sodium chloride into a glass of water. It just simply can't accommodate that much. So there is a certain limit to how much solute you can dissolve in a given amount of water. And the term solubility refers to the concentration of that solute when the solid solute is in equilibrium with the dissolved solute. So what we have here is a reversible equilibrium reaction. The solubility, I'm going to draw a little diagram here to represent it. Let's make sure I don't have a diagram. So I'm going to go ahead and draw it. So you've got a beaker here, and what you've got is you'll have solid sodium chloride at the bottom of the beaker, and it is in equilibrium with the dissolved sodium and chloride ions. And it's what we call a dynamic equilibrium in chemistry, meaning that while you're looking at the solution, you can't tell if anything's happening, but microscopically what's happening is that sodium ions and chloride ions are constantly leaving the solid. Likewise, they're also coming back. And so because the rate at which the ions leave the solid equals the rate at which the ions come back to the solid, there's no net change in the concentration of the ions nor the mass of the undissolved solid. So when we have an equilibrium set up between the undissolved solid and the dissolved ions, the concentration of, say, the sodium or the chloride, due to the stoichiometry, those would be equal, at equilibrium, is called the solubility. And I'll use a lowercase s here. And so we might express that in units of moles per liter, or you could express it in terms of grams of sodium chloride per 100 liters or per 100 milliliters of solvent. There's all sorts of different ways to express the solubility, but it's a concentration when you have an equilibrium established between the undissolved solid and the dissolved ions. Such a solution where you have this equilibrium is called a saturated solution. And the way I think of this is you've saturated the solution with the solute. You've dissolved as much of the solute as you possibly can. An unsaturated solution is where you have not yet reached that solute concentration. The solute concentration is less than the solubility. It is possible to prepare an unstable, supersaturated solution. This is one where the solute concentration happens to be greater than the solubility. However, it's not stable, and at some point that excess solute will precipitate out of the solution. Okay, so a supersaturated solution is not a stable solution. You want to be able to distinguish between these different terms. Let's look at, let's think about gases in liquids. So we'll talk about a solution where the gas is a solute. We'll also later do solids in liquids and liquids in liquids. Okay, so this will be for gases dissolved in liquids. Gaseous solutes obey Henry's law in the so-called dilute limit. That is, when the concentration of the dissolved gas is relatively small. So we have a dilute solution, and the solution will obey Henry's law. The solubility of a gas varies widely for different gases, and that's because of the difference between the interactions of certain gases and water. Okay, so it really depends on how soluble, how much gas you can dissolve in a given amount of liquid, really depends on what gas you're talking about. Okay, so that's one thing. The identity of the gas makes a difference here. Another trend that's important is that the solubility of gases decreases with increasing temperature. And so I like to think of a can of soda to help me remember this rule, right? In a can of soda, you've got CO2 gas dissolved in liquid water. And who wants to drink a soda that is at a high temperature, right? It's kind of flat, doesn't taste good. And that's because the amount of gas dissolved in the water at high temperature is going to be low. Okay, if you want that crisp effervescence of the bubbles, you want to have a cold soda. Okay, and so the solubility of gases decreases with increasing temperature. Henry's law. Gas solubility increases with increasing partial pressure of the gas. And so here we can almost use the same diagram, but I'm going to change it up a little bit. Okay, you can think of this as your can of soda. You've got the water level here, and you've got aqueous CO2 down here, and you've got the gaseous CO2 above the solution, and there's an equilibrium between the two. Okay. There's also a partial pressure of the CO2 above the gas, so I'll write that as PCO2. Now, the larger that partial pressure, the harder the gas is pushing down on the liquid, the more CO2 is going to be dissolved in the liquid. So that's what Henry's law tells us. Henry's law tells us that the solubility of the gas, the moles per liter of gas dissolved here, increases with the partial pressure of that gas above it. Okay? So that's why we've got our soda cans under pressure, right? When you have a pressurized CO2 canister, or can of Coke, or whatever you prefer, the high pressure inside keeps the CO2 dissolved in the liquid. What happens when you pop the top and pour it out? All that excess CO2 starts to precipitate out as bubbles. Right? That's because you've dropped, once you open the can, the partial pressure drops down to 1 atmosphere. And so the solubility decreases. KH here, this is called the Henry's law constant. It's the proportionality factor between pressure of gas and the solubility of gas. And so the units of K depend upon what the units of S and the units of P are. But it's going to be a concentration divided by a pressure. I'll point out that Henry's law breaks down, of course, if the solute becomes too concentrated. Okay, so Henry's law only works in the dilute limit, and then it also doesn't work very well if the gas reacts with the solvent. And even though I've used carbon dioxide here as the example, CO2 is probably not a good choice because CO2 does react with water. But other gases do not. So for example, helium, I don't think oxygen reacts terribly much with just water. Nitrogen, argon, these types of things don't react too strongly with water. Interesting though, if you're talking about oxygen though, if you're talking about the amount of oxygen dissolved in blood, you've got to keep in mind that the hemoglobin in the blood will react with oxygen. Okay, and so Henry's law probably isn't going to work very well if you're talking about how much oxygen is dissolved in blood, just due to that reaction. Okay, so these are graphical representations of the concepts that we had in the previous slide. And so this graph here on the upper left shows the solubility of different gases as a function of temperature. And you can see that at a given temperature, let's say 10 degrees Celsius, these different gases, they all have very different solubilities. And that's because they're just different types of molecules, and they interact with water differently. However, all of the gases, as you increase the temperature, you see that the solubility decreases. So at a high temperature, you're not going to be able to dissolve as much of these gases as you would be at a lower temperature. That's illustrated here in this panel A on the left. You may have noticed that if you pour out some tap water, that you'll see bubbles forming. If you let it sit and come to room temperature, you might notice that you'll see bubbles forming on the sides of the glass. This is due to the fact that as the water warms up to room temperature, the solubility of the air dissolved in the water decreases. And the diagram over here shows us what's referred to as a fish kill, which is a form of thermal pollution where, say, a factory or some chemical or some plant, some factory, something like that, near a body of water, discards its very hot water into the water body, which can cause the temperature around the outlet vent to rise. And you'll see here in the curve for oxygen, if the temperature of the water gets too high, you'll see that the concentration of the oxygen dissolved in the water decreases, and that could choke the fish if the solubility of the oxygen gets too low. On the right-hand side, so this is soda that someone has recently opened the canister of soda and poured it into a flask here, and you can see the CO2 is precipitating out because the partial pressure of the CO2 has dropped from what it was to what it is in the atmosphere. On the bottom right here, we have some naval officers or something like that. They are either undergoing, this is probably a depressurization tank. The idea here, when the divers are very deep in the water, the pressure of the gas in their scuba gear is very high, which means that, and the carrier gas is usually something like nitrogen, I believe. So it's nitrogen mixed with oxygen, or it could be maybe it's helium mixed with oxygen. So what happens is when they're very deep under the water, the pressure is very high, which causes the solubility of the gas in their blood to increase. And if they come up from the bottom of the ocean too quickly, what will happen is the solubility of the gas will decrease rapidly, which could cause essentially bubbles to form in their circulatory system, which can cause a lot of damage, of course. And in order to prevent that from happening, the divers have to come up slowly, and they may need to sit in a pressurized container to slowly bleed off the pressure, so that they don't have this happening inside their circulatory system. That process, when it happens inside the body, is called the bends, and it's life-threatening. And so divers have to be very careful. Here you might see some divers being treated with high pressure oxygen, slowly bringing the pressure down. So that's the graphical examples of Henry's law. Let's do a quantitative example next. So here we've got a problem. It's saying at 20 degrees Celsius, the concentration of dissolved oxygen in water exposed to gaseous oxygen at a partial pressure of 101.3 kilopascals is 1.38 times 10 to the minus 3 moles per liter, determine the solubility of oxygen when its partial pressure is decreased to 20.7 kilopascals. So notice we've got a pressure and a solubility. Then they want us to change the pressure and find the new solubility. So there's a couple of ways to approach this problem. One way is to take the given pressure and the given solubility and solve Henry's law for the Henry's law constant. So you could find KH by taking the solubility they give you and dividing it by the pressure. That's the Henry's law constant. Then you can use the solubility with the new pressure. You can use the solubility equation with the new pressure to find the new solubility. You can also do, and this is the solution that I'm going to show you, you can do what I like to call the ratio trick. You can set up the solubility 1, which you're given, equals KH times the pressure 1. And you can do the same thing for the second pressure and the new solubility. And what you'll do then is you'll divide the top equation by the bottom equation. And you'll see that the Henry's law constant drops out. You don't actually need it. And so now you've got a relationship with these different quantities. Oops, this should be P1. So you know S1, P1, and P2. You need to solve for P2. Then you can plug in the numbers. So the second pressure is 20.7 kilopascals divided by 101.3 kilopascals. The units cancel, times the solubility of 1.38 times 10 to the minus 3, and that's moles per liter. And then you can run that through your calculator. I'm getting 2.82 times 10 to the minus 4 moles per liter. So that is the concentration of oxygen dissolved in water at 20.7 kilopascals. Notice that it's smaller than the amount, than the solubility at 101 kilopascals. So when the pressure drops, when the pressure of the CO2, the pressure of the O2 above the water decreases, the solubility decreases. Part B here is very similar to Part A. The one difference is the units of solubility. So I'm going to go ahead and work this one just because I don't want that to throw you off in an exam, but it's the same idea. Exposing 100 milliliters of water at 0 degrees Celsius to an atmosphere containing a gaseous solute at 20.26 kilopascals resulted in the dissolution of 1.45 times 10 to the minus 3 grams. Determine the solubility when the solute's pressure is 101.3 kilopascals. So the question is, what units should we use to describe the solubility? Well, in the previous example, we used moles per liter, and that's a great unit to use, but you don't have to use that unit. And so what I'm going to do is I'm going to express this first solubility in this problem as 1.45 times 10 to the minus 3, and I'm just going to say it's grams per 100 milliliters. There's nothing wrong with this as your solubility unit. Okay, and that's going to be equal to KH times P1, and you can set up an S2 equals KH times P2, divide the two equations, the KH's cancel out, and then you solve for this S2. So S2 is going to be equal to P2 over P1 times this S1. And so it's going to be, let's see, P2 is 101.3 divided by 20.26. Those units cancel out of kilopascals. And then the solubility, I'm just going to take it to be this 1.45 times 10 to the minus 3 grams per 100 milliliters. And I'm just going to keep this as the unit. Okay, so I'm not going to do anything with that 100. I'm just going to leave it there. Run this through our calculator. And I'm getting 7.25 times 10 to the minus 3. And that's going to be grams of solute per 100 milliliters. Okay? And so this concentration unit is okay too. Nothing wrong with it. Notice that in this problem, we increased the pressure of the gas above the liquid, and the solubility increased. It increased from 1.45 times 10 to the minus 3 grams to 7.25 times 10 to the minus 3 grams per 100 milliliters of water. Let's see. These two problems, there's really no difference between these problems and the ones that we've done previously. The only difference is that doing the solubility in grams per liter. Okay. Notice 27 grams of acetylene dissolved in 1 liter of acetone. And so just use grams per liter as your solubility unit. So I'm going to leave these two problems as an exercise for you to try on your own. And we'll move on to the next part here. So what we've just done are solutions of gases in liquids. And so this slide deals with solutions of liquids in liquids. The rule for liquids, for liquid solvents, is that like dissolves like. Okay, and what does that mean? Well, this refers generally to the polarity of the solvent and the solute. And so polar solutes dissolve well in polar solvents. Nonpolar solutes dissolve well in nonpolar solvents. So in order to make use of this rule, like dissolves like, you need to be able to assess the polarity or nonpolarity of a simple molecule based upon its chemical formula. And so this was an exercise that you learned how to do in Chem 120, General Chemistry 1. And it took several chapters of material in order for you to understand how to do that. And so let me remind you of what I'm talking about. So in order to make use of this rule, you have to be able to take a chemical formula and you need to be able to convert it into its Lewis structure. Now recall that the Lewis structure is a two-dimensional flat representation of a molecule. It doesn't really tell you anything about its three-dimensional structure. So once you have the Lewis structure, you need to be able to get to its VSEPR geometry, valence shell electron pair repulsion geometry. Now this is a three-dimensional structure, okay? And based on the VSEPR geometry, you can determine whether the molecule is symmetric or not symmetric, so symmetry. Based on that symmetry, you can determine whether it's polar or not nonpolar. I'll say symmetry and asymmetry. you'll recall that the asymmetric structures are polar and the symmetric structures are nonpolar. Okay, so there's actually quite a lot of Gen Chem 1 material that goes into this process. And so then finally the new part, the part that we're learning about in Chem 222, is then like dissolves like. So very often I find that students have lost track of this skill, in which case I'm going to encourage you to go back through some of the Chem 120 material in order to be able to utilize this new concept. I'll just run through a very quick example. Let's think about carbon dioxide. Okay, so here's the chemical formula for carbon dioxide. The Lewis structure you would need to arrive at is this one. Its Vesper geometry is going to be linear. It is symmetric. Therefore, it's going to be nonpolar. Then we'll ask ourselves, do you expect CO2 to dissolve better in water or a nonpolar solvent like CO2, something like that? Not CO2, I meant to say benzene, something like that. And so based on the rule, you would predict the nonpolar solvent would be better. So you need to be able to figure out, is a simple chemical, like given the chemical formula for a compound, is it a polar species or a nonpolar species? And then you need to be able to apply this concept. Here are the three terms that we have down below. Miscible. This refers to liquids that mix together in all proportions. So water and ethanol is an example. Another example would be water and ethylene glycol. That is the ingredients within antifreeze coolant. The term immiscible refers to liquids that do not mix together. So an example would be oil and water or oil and vinegar. Don't mix together. They make good salad dressing, but you have to shake it first. We also have something in between, partially miscible. So here we've got a test tube that's full of bromine. Here's a test tube that's full of water. If you mix them together, the two liquids separate and form layers. However, you can see that there's a little bit of bromine dissolved in the liquid layer, and there's a little bit of water dissolved in the bromine layer. Okay, and so we describe these as partially miscible. Okay, it's pretty complicated stuff. What kind of solutions form and what the solubility should be and all of that stuff. Nevertheless, what you need to know the basic idea that like dissolves like. You will not have to predict whether or not two liquids will be partially miscible. I just want you to know what partially miscible means. All right, the last type of solution we'll talk about is solids dissolved in liquids. And what we're going to think about is the temperature dependence for solid solutes. In particular, I think it applies to all solids, but it's generally for ionic solids that you're going to see this. You're going to see this in your problems and test questions. So the solubility, the temperature dependence of the solubility of a solid solute can either be to increase or decrease as the temperature increases, and it depends. It depends on what type of solid you have, and there's two cases that you need to worry about. There's the case where the dissolution process is endothermic. That is, for a compound like potassium nitrate, the enthalpy change for the dissolution process is greater than 0. For this type of ionic compound, the solubility increases as the temperature increases. The other type that you need to worry about is when the exothermic process is, when the dissolution process is exothermic. Okay, so here for this cerium, what would this be? Cerium 3 sulfate. It's an exothermic dissolution process. In this case, when the temperature increases, the solubility of the ionic compound decreases. Okay, so these are the two rules. So in order to predict whether or not the solubility of a solid solute will increase or decrease with temperature, you need to know the sign of the delta H for that process. Okay, and here's one way to help you remember the rules. I'm not real big on memorizing rules, especially rules like this, because it's so easy to get them backwards. I usually try to associate with a particular process, which I find easier for me to remember how to do. So there's two cases here. Let's consider the endothermic case. So we've got some reactants, we've got some products, and in the endothermic case, we can think of heat, which we associate with temperature, as a reactant. Okay? And now what I'm going to show you is this sort of, it's a balancing act. It's a teeter-totter or visual approach to dealing with questions involving equilibrium. Okay? And so you need to watch what I'm doing here. When you increase the temperature, that has the effect of pushing, in this case, when the temperature is on the left-hand side, that has the effect of pushing you towards the right-hand side. Right? So you're going up. To maintain equilibrium, you need to go over. Okay, so think of it visually. So think of it as increasing the temperature is like a push to the right. So when your temperature is on the left, when you increase it, you push to the right. For a dissolution reaction, that has the effect of increasing the amount of dissolved ions, right? If the products are the dissociated ions and you push the reaction towards the products, that means that the solubility of the reactant is going to increase. You're going to be dissolving more of the potassium nitrate in this example here. You get the opposite effect if you cool the solution down. If you cool down, that has the effect of pulling back to the reactants. Okay, so when you increase the temperature, you push to the products. When you decrease the temperature, it's like pulling towards the reactants. Okay, and so when you pull towards the reactants, that's going to decrease the amount of dissolved ions. That's going to decrease the solubility of the potassium nitrate. Okay, so for an endothermic reaction, if you increase the temperature, you dissolve more compound. If you decrease the temperature, you dissolve less compound. Sorry, if you decrease the temperature, you dissolve less compound. The same technique works for the exothermic reaction. It's just that the heat term is on the product side, and we associate that heat term with temperature. Okay, so here, if you increase the temperature, that's going to push you towards the reactant side. Okay, so for the exothermic reaction, increasing the temperature is going to decrease the solubility. And that's the case for this cerium 3 sulfate species. Conversely, if you decrease the temperature, that has the effect of pulling you towards the products. So that's going to increase the concentration of the ions. That's going to increase the solubility. Okay, so this visual trick, it works both ways. Whether it's endothermic or exothermic, you just need to know endothermic means that the heat term is over here. Then you can figure out, okay, if I increase the temperature, what's going to happen. If it's exothermic, it's on the other side. Now we're going to come back, so we're going to use this trick in forthcoming chapters when we start really hitting equilibrium hard. And so this is something this type of visual trick that I'm going to use quite a bit. Here's a graphical example of what we're talking about. For most compounds, most solids, when you increase the temperature, the solubility increases. Look at sugar. It really goes up quite a bit when you increase the temperature. For that potassium nitrate, wow, it really shoots up. Other compounds like sodium chloride, not so much of an effect. And so I haven't told you how to predict whether or not it will be a big effect or not, but for different compounds you get different effects. For the cerium 3 sulfate in this case, you see that it actually decreases. Okay, and so that's unusual for a solid dissolved in water. Most of the compounds you see here, the solubility increases. It just depends. Is it an endothermic reaction, like it is for all of these guys? Or for the cerium sulfate, is it an exothermic dissolution reaction? And that just depends upon the nature of the ions. You can use this temperature effect as a strategy for preparing supersaturated solutions. And so let's suppose you wanted to make a supersaturated solution of potassium nitrate at 40 degrees. Okay, and so at 40 degrees, the solubility of potassium nitrate is somewhere like, 65, maybe 70. We'll call it 70 grams per 100 grams of water. What you do if you want to go beyond this solubility at 40 degrees, what you'll do is you'll heat up the solvent. You'll heat up the water to, say, 80 degrees, and then you'll dissolve as much potassium nitrate as you can. So you'll saturate the solution at 80 degrees, and then you'll let the solution slowly cool without disturbing it, without agitating it. And what will happen is the solution will cool, but the concentration of the dissolved potassium nitrate will stay the same. Okay, so you'll have like a really high concentration of sodium nitrate, but it's unstable. And if you disturb the solution, for example, if you add a glass rod to it that's got a scratch in it, or if you drop in just a really tiny crystal of potassium nitrate, what will happen is that the solution will suddenly precipitate. That is, that all of the excess sodium nitrate will crash out of solution, and the solubility will drop down to what it's supposed to be at that temperature. And so you'll get a huge amount of solid coming out of solution all at once. And it's a pretty dramatic effect. I think the textbook has a link to a video showing this process for certain ionic compounds. Well, I'm going to go ahead and stop this video here, and we'll pick up with the section on colligative properties in the next one.